Welcome to chapter 15 on oscillatory motion. This is number 62. And we're given a particle of 4 kilograms that is moving on a spring of force constant 100 newtons per meters. And the amplitude of its oscillation is 2.00 meters. And then we have a 6 kilogram object that is dropped on top. And what we want to find in part A is the change in amplitude, in part B the change in period, in part C the change in energy, and in D why the energy changes. So let's draw our figure out. So what they're saying is we've got a little spring like this, and then this is my 4 kilogram block. And then we have a little 6 kilogram thing dropped on top as it's in its equilibrium position. So the first thing we're going to know is they collide inelastically, so they're going to pretty much stick together. So the final is going to look kind of like this. It's going to be the same thing, just 10 kilograms. Okay, so if we look at this in that way, we know that the mass is now 10 kilograms for the oscillation. And we also want to look at the change in velocity. Okay, so normally we have 1/2 kx squared is equal to 1/2 mv squared, because it's a conversion of energy where this is the max potential and this is the max kinetic. So let's just plug this in to find out our original. We'll give an amplitude 2, square that, halves cancel out, 4.00 kilograms, and then we have velocity squared. So now we see that the force cancel out, so pretty much we get a velocity of 10 meters per second.
Yeah, because you divided 4 by both sides, square root of 100 is 10. Good.
Precisely. So you get v equals 10 meters per second. Now we're going to have to do a bit of momenta calculations. So before, what we're told is pretty much that the objects stick together, and we can assume that the vertical drop, that momentum is just lost into the ground, so that's not important. But the horizontal momentum is what we care about. So initially, our momentum is going to be 4 kilograms times 10 meters per second, right? And our final is going to be 10 kilograms times v. So v is 4 meters per second. This is 40 divided by 10.
Okay, because that is the conservation of momentum.
Precisely. So this is conservation of momentum right there. So now we have this, and now we can recreate our earlier conservation of mechanical energy. So we go back here, 1/2, now our mass is 10, so 10 kilograms. 4 meters per second, the whole thing squares to 16 meters squared per second squared, so that's 1/2 mv squared right there. And we have our 1/2, 100 newtons per meter, amplitude squared. So these are going to cancel out. Now, so pretty much we get 160 kilograms meters squared per second squared over 100 newton meters. So thus we get 1.6 meters squared is our amplitude squared. So we want to take the square root of 1.6. So let me get out the calculator.
Just as a quick recap, what we did is we dropped it on top. We did the conservation of energy, conservation of momentum, back to conservation of energy, got here. The square.
So here we go. The square root of 1.6. So that's 1.26. We'll leave it at that. And we know that initially it was 2.00 meters. Now we're at 1.26. So our change is 2.00 minus our answer, which is simply 0.74 meters. And now we'll continue to part B, which will go on the back. So we know that the period of oscillatory motion, which we know earlier, given on a spring, is this. That's the formula you will need to know, and that's how
that equals the period.
So this is our initial period, which I'm going to indicate by T0. It's 2 pi. What was our initial mass? It's 4 kilograms. K has always been the same. So in this scenario, we get essentially 4 over 100. That's 1 over 25. When you take the square, that's going to be 1/5. So we'll take the square root of that. It's 1/5, and we're going to multiply that by 2 times pi to get essentially a period of 1.26 seconds. Remember, period is measured in seconds. Then our T final is going to be 2 pi. What's our new mass? Our new mass is 10 kilograms divided by 100 newtons per meter, because spring constant stays the same. And we're going to try this again. Divide this by 100. Take the square root of that. And multiply by 2 times pi. So our new period is 1.99. So 1.99 seconds. So our change in T is going to be 1.99 seconds minus 1.26 seconds, which is equal to 0.73 seconds. Cool. So now we'll continue to part C. Now part C asked us for the change in energy. So what is the change in total energy? Now we can do that as stated earlier. We actually use that in our earlier calculations. So remember how we said we'll just go by 1/2 mv squared, because that is probably the easiest way for us to do this. So initially we had 1/2, we had 4 kilograms, and earlier we found our velocity to be excuse me,
Bless you, Parth.
10 meters per second. So I'm going to plug that in. So that's 10 meters per second squared. So that's going to be our KE, or our just mechanical energy initial. And that's equal to, so let's plug this in our calculator, 100 times 4 divided by 2 happens to be 200. So it's going to be 200 joules, because energy is measured in joules. Our mechanical energy final is 1/2. Now we have 10 kilograms as our mass. But we also found that because of conservation of momentum, there's going to be 4 meters per second, which we did earlier. So just, if you need to check back on that, you can look at that. And now, I'm going to plug this into our calculator to get 80. So now we have 80 joules. So what's our change in energy? Simply 120 joules. You can say it's negative, or but 120 joules are lost. Okay. Now part D is a bit conceptual. It's asking us why this energy is lost. Now first of all, we know it's not an elastic collision. So anything that isn't an elastic collision does not have conservation of energy. And we know that. We're going to start by that. Now when we look into why, there's a couple of reasons. First of all, if you've noticed, when there's collision, you hear sound. When you hear 2 billiard balls crack, there's sound. That's sound. It's my great drawing of sound. It's very beautiful. Sound is a way of releasing energy, actually, because you need to give off those vibrations. That's one way to release energy. Oftentimes, light is emitted. In this case, we're not going to have light emission. And then another way, another change in energy is when it increases in internal energy. You have a delta E internal. So when they stick together, this new block has like an internal energy. Sometimes that can lead to a change in temperature of the block itself, but I mean, we'll just stick with a change in internal energy, and we'll stick with sound. Those are going to be our key points right there. So that's that.
Wow, only 2 pages. Great job, Parth.